Next speaker is Dennis Sandler from NVIDIA on incremental live video processing in IP-based GPU leveraging software. Dennis?
Okay, so this talk is about an optimization that applies in cases when your incoming media is paced. So much like the previous talk was talking about ST2110, when all your pixels are coming in at regularly paced intervals. So at first I'll introduce kind of the background, the motivation for doing this in the first place, and then I'll go over the media pipeline itself, the one that we're using in order to get the results, which will be the last section. Before that, I'll kind of explain the theory behind why performance is increased when we apply this optimization. So in a recent trend in broadcasting, if before media functions when were purely were just fixed function hardware appliances that are, if programmable maybe a little bit, things are now moving towards commercial off-the-shelf hardware. So regular general purpose computers, usually this is a reference to servers, but for the purposes of this talk, it could be a workstation, just the same CPUs, GPUs, memory that's running on your workstations, on your laptop. And as a result, the responsibility of the media function itself goes into software. As such, software being very flexible means that, you can repurpose the same piece of hardware, the same unit for doing, various kinds of media functions. You don't just have to buy, a piece of hardware and know that it only has some range of specific functions that it does. Furthermore, it's scalable. So you might purchase a server and it's got so many CPUs, a GPU, so much memory, and as a result, you're not limited to only doing a specific thing. You can kind of subdivide with Docker, Kubernetes. You can allocate a specific subset of CPUs, GPUs, memory, and then you can do, various things on the same system, and you ought to in order to exploit the economy of scale. So, that's all well and good that, software allows you to do so much, but at the same time, that means that there is added responsibility. So it's no longer just, having to set up the hardware to do what you want to do. Now you have to write the software and make sure that it uses the hardware economically, efficiently, and therefore economically. So software needs to meet the media flows, throughput and latency requirements. And even beyond that, even if it does meet something, it is very important that it goes even beyond those requirements, that you want to make sure that the latency is in fact minimized. And this is where we get into the economy of scale, because we're going to want the same, you're going to want the same server with a unit of infrastructure, so some amount of CPUs and GPU, maybe many GPUs, memory. We want them to be able to run as many streams, run as many media functions as possible, because, every piece of hardware costs us money. So the fact that they're divisible, furthermore, they might extend across the network. So this is again circling back to why you want to make sure they perform at their best, so that you can fit as much software into one sort of unit of hardware infrastructure as possible. Every single CPU core, every single GPU, every gigabyte, megabyte of memory, that has a dollar value associated with it, whether it's, power costs, whether you're running the data center on your own, whether it's in power costs, or more than likely if you're subscribing to, an AWS instance, some other cloud provider, you're paying per hour for every single unit, so you better make the most of it. So better make the most of it, so you have, the more streams you can run per dollar, the better. And so going into this optimization, so most of the time, and most software workflows, because they have to or just because they do, when you have an incoming frame, some incoming media source, at this point, most of the time you wait for the entire frame to arrive before beginning to process it. Now, as we've heard from the last talk, ST2110, for example, the image data comes in very gradually. Every single packet is paced in a very predictable manner, and, we know exactly when we're going to get which pixels, or at least we try to know exactly when we're going to get each pixels. And this predictable flow of data allows us to capitalize on it by processing not the entire frame, but part of the frame. So we say, like, the first part of the frame arrives, we begin processing it, and as we're processing it, the next part of the frame arrives in parallel. So we can kind of pipeline this and not have to wait for the entire frame, which reduces latency, and I'll demonstrate this in an illustration. In many pipelines, ultimately you want to encode we get an uncompressed frame. In this case, we want to encode it into some compressed formats, AVCH, EVC, AV1. Because those three, they support slice-based encoding. So, which means that, say you take an image, you break it down into some number of slices, and each of those slices can be encoded into the respective compressed format independently of the other slices. So what that means is we receive the first slice, we can begin encoding it and not worry about the fact that, we received the second slice. That might be, it's not going to change any state as we're encoding because they happen to support slice-based. Now, other part of that is, the hardware we're dealing with when we're processing the media. So for ST2110, there are high data rate NICs, which allow you to receive large uncompressed frames over a high-speed network. And on the other part of the pipeline, you have GPUs, which are very suitable for processing imagery. So processing pixels, since they can exploit mass parallelism, you can process pixels in flight. And oftentimes something like color space conversion, cropping, other simple operations, they're highly parallelizable. Now, combining them together, some high-speed NICs are also RDMA capable. So RDMA usually refers to remote direct memory access. In this case, we're not actually quite doing that, but the idea is that you have a NIC and you have a GPU, and as an uncompressed frame is coming in, as long as the NIC is RDMA capable and it can interface with the GPU, you can actually get that data directly into GPU memory. So it doesn't have to go through, the added latency of going through system memory, of going through the operating system kernel. It can just make its way directly into GPU memory, and it's ready to go to have a CUDA kernel or a shader or whatever for the GPU to start processing it. Furthermore, GPUs nowadays also have encoding engines. Now, these are actually separate hardware units on the chip from those that are processing the pixels for things like color space conversion. And not only are GPUs suitable for it, but it's a very good idea to use them because it frees up a lot of CPU cycles, and you still, in a real pipeline, you're still going to need to use CPUs. You need to parse the encoded bit stream. You're going to need to mux the data into a container format. You're going to need to then transmit it, and the logic behind slice handling as well. So now I'm going to go over the pipeline in this case that we were running. So everything starts with a video source, a source of ST2110-20. -20 is the video part of the standard. Comes in to the NIC. Afterwards, as I said, thanks to RDMA, it can make its way directly to the GPU. There, two things happen. CSC, color space conversion, which is more often than not needed in order to prepare the frame to be able to encode it using the encode engines, because they only accept specific formats, and you may happen to have, a totally different sampling color space coming in through ST2110. Next, you need to parse the compressed bit stream, mux it, possibly payload it into something like RTP as well, depending on exactly what it is that you want to send out. And finally, once you have everything, you send out something, could be an RTP stream, SRT. In this particular case, we've worked with RTP. And so this is the pipeline. Now, this is how the pipeline looks, say if you're not doing any slice-based encoding. Here's a kind of illustrative animation of how this would look. So on the top, we have kind of over time, we see how busy the GPU is and when it's busy. So assuming we have like a 60 frame per second video coming in, this is what no slicing looks like. So frames coming in, and in the meantime, the GPU isn't doing anything, even though it's the next in line to do something. As soon as the frame arrives, we have the frame, and then the next frame is going to come in, and all of a sudden we have a spike in having to process that first frame that came in. So, over the course of, 2 frames, we only have this one spike in GPU activity, and yet we're paying for, the whole time, for having it around the whole time. Now, the same illustration, say we divide it into 3 slices. Now, this is how it's going to look with 3 slices. So first slice comes in, we still have to wait for the first one to come in. As soon as it comes in, it's in the GPU, and we can process that slice as we're waiting for the next one to come in. And same applies for the next frame. We are processing it as that one comes in and the final one. And as we're doing that, we can go ahead and receive the next frame, process it, the next frame, and process it. So now you can see like the workload, there are still spikes, but at least now they're spread out over time a lot more than they were before. And same goes, just for the purpose of completeness, here's a scenario with 6 slices. Comes in, the next one comes in. So same principle, just more slicing. And so here, I'm obviously showing a GPU busyness. You could differentiate between, are the CUDA cores busy doing the color space conversion, the encode? This is for the purpose of illustration. I'm kind of presuming that kind of the busyness of both of them, you might say for that relatively short burst of time that it takes to process the slice. And so this is the pipeline. This is how the optimization works. Now I'm going to go through the 2 kind of operations on the GPU and how they look as far as performance. So the first one is the color space conversion. So say we're dealing with 1080p. Here we have CUDA cores working, and so these are just general purpose, arithmetic units, load, store, registers, and there's a whole lot of them, so you can process a lot of pixels in flight. So let's say, I have the dotted lines here. Let's say the first level of dotted lines is the workload that it takes to process 1 frame of 1080p. Now, one thing, this is kind of exaggerated. I don't know how many, maybe the highest end GPU can actually get that many HD frames in flight, but principle is still the same. So say we can process as many, HD frames in flight as there is capacity for on this image. So first, one stream that we have that's coming in is, we have 1 stream, and these are the processing spikes right when it was received. So now on the same hardware, we don't just want to run 1 stream. We want to run as many streams as we possibly can on the same infrastructure that we're paying for. And we certainly have the capacity to run some number of streams. So second stream might come in, with its own phase. Obviously, you never know. These are totally independent streams. They might be serving totally different, different clients down the road. So the phase is completely random. And as we add streams, these can fill up, given their phase that they come in, they fill up all the CUDA cores that are available. And again, like I drew them on the same level, but that's not necessary. They don't necessarily need to be on the same level. It could just use up whatever, CUDA cores happen to be available at the time. And so there's a lot of capacity, especially for something like color space conversion. It is only after a point. Now see how I purposely kind of filled up 2 columns, as you can see here. So if, for example, the next stream that we try to launch just happens to start processing here when a bunch of other streams have already started to process, this is when, it currently doesn't have the resources to proceed. And so as a result, it needs to push it back, given one of the chosen CUDA cores that will be executing that needs to be pushed back, and only then the workload has to be processed. And so that is going to add a latency right there. So, next, say if we're dealing with 4K UHD. So then what changes in this image is instead of, having the same, we no longer have the same capacity to process HD frames. Now, say like there's 4 times as many pixels, so, it might take, with operation like color space conversion, takes roughly 4 times, as many resources. And so same principle here. We fill up everything gets filled up in the same sort of manner. Just as this. Again, only difference is less capacity, and so it'll take less streams in order to saturate this. And so, what happens when we slice? So what happens when we slice, and in the previous diagrams, I actually, I neglected to say that, given that there's a first frame to the left, it just makes it easier to illustrate. But this is, again, no slicing. Now, when we slice, here's what happens. So obviously, we're going to have not one workload, but now 3 workloads per frame. But also, the capacity goes down by 3. So again, the grid changes, and now we have these slices being processed. And again, as we add streams, it's going to look exactly the same. We just fill it up. Now, next is encoding. So encoding works a little different. If color space conversion uses these general purpose kind of CPU elements that you find on a CPU, encoding is different. Encoding, it's a separate ASIC, and the only kind of parallelism there is you may have 2 encoding engines. So some GPUs have 1 encode engine, a lot have 2. So some of the recent ones actually have 3 now. There's one that has 4, that is to say. And so, but when it comes down to it, if you have 1 stream that's going to take up 1 engine, and there's no subdividing the engine, its next stream is only going to start getting coded after the first one is done. So 2 NVENC engines, 2 streams. So let's go through the 1080p case again. So we have 1 stream. The next one, probably just round robin to something that's more freed up. But as before, it would fill it up. Just the capacity is 2 this time. And the same principle applies. Eventually something will get pushed back. I'll get into more of that. Now, if we move on to 4K, notice how no longer, our capacity is we still have 2 encode engines. So if you're encoding a stream, you're encoding a stream on an engine. That doesn't change. Instead, it just takes longer to encode the stream that's now, 4K rather than HD. So, and now when we slice that, all of a sudden, we, just as before, we get the different slices all more spread out than before. So yeah, obviously, I offset it immediately after, 16.67 milliseconds. Obviously, it takes a little bit of time to color space convert it. So, but in any case, it's still spaced out, presumably the same, similar way. So, so now, just to kind of illustrate what happens when there's another potential stream that takes up the encode engine. If it happens to start over here, far away from any processing of the other stream, that's fine. That's not going to add to our latency. The first stream is going to be just fine. If it starts here, that's also perfectly okay. If it starts anywhere here now. If it starts here, if it happens to start at the same time when another stream was supposed to begin encoding, no longer can that first stream start encoding at that time. It would have to get pushed back, and your latency as a result gets pushed back. Now, let's take a look at what happens. So, anywhere on this whole frame, if anywhere on the frame you have an overlap of another frame, you get latency. So now let's see what happens when you slice. When you slice, sometimes a little different. So again, this is not bothering anything, perfectly okay. And this, in fact, is also perfectly okay. And yes, this is going to get pushed back, but you don't really care because there's still plenty of time until the last slice gets processed. And it's only the last slice that matters because you're still not increasing the overall latency of that one frame. Same applies for the second, and just any slice other than other than the very last slice. And that is the only slice, the last slice, that it requires you to push back and add to the latency. So you kind of look on the upper right, and you can see that when you're doing slices, it's only 1 divided by the number of slices of the area, sort of the time duration of the frame that you have to overlap on in order to increase the latency. So already you have a lot more leeway when doing slices. So that is the theory behind, how this helps decrease latency. And now let's get into some practice, into the results that we've observed. So first, we want to measure the latency. What happens when we run one stream? And on the top left, I've roughly kind of described what hardware this is running on. 14 CPUs happen to be free on that machine, was 1 GPU. And so 6 experiments, typical resolution. So just looking at here, so with no slicing, this is the added latency. So this is beyond, so obviously sooner or later at some point you still have to wait the 16.67 milliseconds in order to see the entire frame at some point or another. But when you're processing the frame, you're adding some latency between the color space conversion, the encoding and the parsing. So you're still adding latency. Now, so if you look at the percentages here when you start slicing, it looks pretty good, right? We're getting like half of the latency we did without slicing for HD 60, which is great. Same applies for even more if you do more slices. That's all good and all, but if we circle back to, the economy of scale and streams per dollar, and just looking at this, when it comes to HD or 4K, well, sure, we can process a frame in 1.4 milliseconds less, but what's 1.4 milliseconds going to do in cases where you have, latency budgets of 33 milliseconds or maybe even 100 in some cases? That reduction of 1.4 milliseconds is not really going to make a difference in the grand scheme of things. And the only place where this, I think, does make a difference is when you're dealing with something like 8K. On this setup, when you're not using slicing, not only is your latency through the roof, but this is obviously dropping frames, because in the pipeline that we have, there are kind of 3 parallel steps with queues in between. So that means that for 30 FPS, you can't go over 100. There's just no way. And this goes over, so you're definitely dropping frames here. And just the fact that you're slicing something, as restrictive as 8K, all of a sudden you can do that on this machine, which is nice. So I'd say the only merit, I guess, in these results would be for 8K. The other ones, great, but it's not really a big deal. The real question is how many such streams can we run on this machine up to the point where, we go over our latency budget that we set out for ourselves. That's the real question, because that's going to define exactly how many dollars we pay per stream. And that's important. And that's the next set of results. So here we see that, yes, slicing, the decrease in latency does allow us now to run. So here, exactly like what these experiments are, we assume that we have a 1 frame latency budget. So for 60 FPS, we can go over an added latency of 16.67 for any of the streams. And this is what we get as a result. So it's not bad. One remark for 8K, for example, 8K 30, we can still, where's the laser pointer on this thing? So, here it is. So the 8K 30, we can actually get as much as 2 streams when we're doing slicing by 2. Same with 3. 8K 60, well, if we're slicing by 4, then, you can actually run a stream on this setup, which is nice. Other than that, 2-3 slices found as good. So the benchmark itself, this is a fully functioning pipeline, yes, and there's a lot of moving pieces, and there's a lot of areas for optimization right now. Not even related to slice-based necessarily, just general. Some optimizations are quite simple. There's still some work to do, and hopefully you can get better results than the ones we have now. So yeah, that's pretty much it. So basically, and again, like as I said in the very beginning, this optimization applies when your incoming media is paced. So when you have to wait for it, you can capitalize on the fact that, you're not going to get it until, 1 divided by the frame rate. Now, if you're not so ST2110 is just a great example of that. Now, if you're not using something like ST2110, most of the time, like if you can do all your processing on one physical machine, then this is pretty useless. Like, for example, if you have a bunch of if you're ingesting a bunch of, H.264 streams from people like live streaming themselves or something, then you got to decode that. And then, when you're decoding something like that, there's no way to tell what's going to come in before what. I mean, yes, they're streaming at like 30 FPS, but when you're decoding the null units, or I'm not a coding expert, I'm not aware of a way to tell, which ones are going to account for which pixels and if it's going to be in order. So you can't really do slice space. You really need the whole frame up front. Where it makes a difference is in cases where when you're scaling out and you have more than one machine doing this. So if you have a second machine that say you're doing something you want to do AI, where you actually still happen to need the frame up front for many algorithms, not all of them. You decode the frame, you do your inferencing using the CUDA cores, the tensor cores, and then say, like you've already expended so many CUDA cores that you can't really do color space conversion for that same amount of streams. Your best bet, since you're working in, a high-speed network, you can send that over to another physical machine that can then do something similar to this. Since you're sending it over, you don't want to drop frame, but you still want to send over UDP, so you do still want to paste the packets. You don't want to burst them because you're going to drop a lot of frames in your high-speed network. You still want to paste them, but you don't necessarily have to paste them at the frame rate. You can paste them at something faster. But the fact is, and your chances are you're still going to be using RTP between, two machines on a high-speed network, because that's one of the simplest ways to pass uncompressed data. So in that case, there is still potential for this optimization. And again, this is a more complicated setup. It's not as straightforward as the one that we went through. And it'll probably deal with a heterogeneous setup. You may want to combine different GPUs, one that doesn't have any encode, and we have those, and that's suitable for AI, but one that does have encode engines to do the final encode and egress. And another sort of side effect of slice-based encoding, it can offer better resilience once you actually have it all, once you've encoded it, because the thing is, like, if when you send your final encoded stream, if you happen to drop some packets, that'll only affect the visual quality of that slice to which those packets pertain, because the packets were encoded independently. Whereas, have you not been slicing and you're dropping frames, then it's much harder to tell what part of the image and how much it's going to affect. That's another side effect. That's it. Questions? Yeah. Yes. So if it gets significant, yes, there's going to be overhead. And furthermore, so if you saw, like, in the results, and I should scroll back to them. Where's the 4? Okay. So even though, like, you'd think that, why would, the performance fall below no slicing to 14 slices for HD at 60? The reason is, as I said, like, there's areas of optimizations. Currently, I'll just say, like, when we're doing more slices, there are more threads that need to be running. So that's one. That doesn't have to be the case, but if you get up to something like 16 slices, yes, but if you get to something that's like 16 slices, yes, there's going to be inherent overhead, because GPUs are good for mass parallelism. So you do want to still give it a nice chunk of processing. So if you're going to be, like, doing 2 scan lines, that might just not be worth it. The other thing is, like, there's only so much slicing you want to do, because slicing when you're encoding has quality degradation. So for 2 slices, we've seen in our some other work, for 2 slices about a 1% drop in PSNRs. 3 slices about 4. 4 slices, don't quote, but I think it's something like 12 to 18, but I'm not entirely sure. Okay, did I answer your question? Okay, I think somebody had their hand raised.
Yeah, hi, I'm Jill Boyce with Nokia. Use of slices can reduce coding efficiency, like there's extra bitrate efficiency and sometimes leads to subjective artifacts across the seams of the slices. So, but like some of the other things you're saying, like the color space conversion, I mean, that could be done in parallel regardless of whether or not you're actually encoding with slices, right?
It is done in parallel on the GPU, yeah.
But I'm just trying to understand if you've like looked at the implication, because it seems like if you increase the bit rate a bit, then by using slices, then some of the efficiency of the loading would also go down.
Are you talking about the compression ratios?
Yeah, I mean, well, like with the compression ratio is going to go down, so the bit rate's going to go up, so you have more pixels, more bit rate to process.
Are you asking?
So does that affect this? Is this being used in practice with the slicing, given the sometimes subjective effect?
Yeah, so just slicing, not necessarily just like this happens to you slicing. There are other methods, like when we released the the ADA generation boards, there's another optimization, like where you would have a frame come in, maybe a large frame, and in flight you would actually slice it by two, and on two separate NVENC engines you would process these slices. So we do slicing, and there is a drop in quality, but in many scenarios, from what we understand, it's tolerable.
Okay, thank you.
I'm sorry, I'm going to have to do time management here, so thanks, Dennis.